All right, everybody. So 38 says, given the vertices below, find the side lengths and measures of the interior angles for the triangles below. So what I'm going to do is I'm going to start by resolving these into vectors. So I have the vectors xy, I'm going to have the vector yz, and then the vector zx. So xy is going to be head minus tail, and then head minus tail. YZ is going to be head. Wait a minute, hold on a second. Oops, that's the wrong order. So it's head minus tail, and then head minus tail. Okay, and then head minus tail, and then head minus tail, and then head minus tail, and then head minus tail. Everybody's okay with that? And it doesn't really matter whether you did head minus tail or tail minus head for the magnitude piece, which we'll do first. Uh, 169 plus 121 is 190, I think. And 49 plus 36 is 85, right, Prater? Oh, 290? Yeah, thank you. Everybody so far so good? All right. To do the angle between two vectors, I'm going to use that angle between two vectors formula. Now, I have to be a little bit careful with how I'm doing that, as if we remember back for that formula, let me go pull that up real quick. So my formula is, oh boy, that's not where I was supposed to go. So that was the formula. But if you remember, the way this had to work was that, like, you know, like these had to be my vectors u and v. So if I think about the picture that I have here, we'll just kind of plot this real quick. So x is like here, y is like here, and then z is like here. So you have this like real oblique looking triangle. So we're going to find these angles one at a time. So let's say I want to find this angle first, right? So that's going to be the vector xy and then the vector xz. So xy we have already, but we have the vector zx instead of xz. How do I get zx out of x, or how do I get xz out of zx? Well, I could redo it, right? I could do head minus tail, and then head minus tail. What do I notice that this is? Yeah, I just multiply both by -1 is going to give me the same thing. So I'm going to use those. So cosine inverse of -6 times 7 plus -5 times 6. And then the magnitudes I already have, right? Because those magnitudes are going to be the same whether they're going forwards or backwards. So I'll just plug that in. So I get about 179 for angle X, which based on my picture, does that seem reasonable? Probably, right? That's looks almost like a straight line, those 3 points that I drew. So I'm not surprised that like that angle X should clearly be the biggest angle, and it's darn close to just being a straight line. Zoe?
I got the same thing too, but like I did like the side angle thing.
Sure.
Did that work?
It's the same thing. That's how we derive that angle between two vectors formula.
Okay, but I did it like where it's like cosine of c is c squared.
Yeah.
Does that work?
If you remember, like when we derived that, like the angle between two vectors, we started with the law of cosines as our derivation. So all you're seeing in that formula is just like a special case of the law of cosines. So yeah, of course that should work, right? That's what we use to prove it. So for angle Z then, we're going to need the vectors xz and then zy. I should say zx and then zy. Okay, well, zx we have, and zy, now we understand immediately how to get zy out of yz, right? So angle Z is then going to be cosine inverse -7 times 13 is 91. And then -6 times 11 is 66. And then the ZX had magnitude root 85. And ZY had magnitude root 290. And I should expect this to be a quite small value, right? Something less than 1. In fact, something less than 0.8. Since this guy still has to be a triangle. So that's about right. 0.36 seems okay. I'm going to add an extra decimal point here. And then angle Y we get for free. Because we just use triangle sum to get that. Tessa, is this okay?
Yeah.
So 0.43 for that one. And all those magnitudes that I left as radicals, I mean, I type that through and make a decimal out of it if you want. That's fine. I wouldn't worry about reducing radicals. I would just turn it into a decimal. I just left it as radicals because it was going to be easier to put it to the angle formula. It's like, why make more work for myself kind of thing. Elena? 47? Sure. All right. It says a crate of negligible weight is being pulled up a ramp at an angle of 38 degrees with a force of 120 degrees. The ramp has an angle of elevation of 25 degrees. What is the amount of force being directed up the ramp? So if we just kind of sketch ourselves a picture of what's going on. So we have like our ramp here, where that's 25 degrees. And then we have some pull vector going on at 38 degrees, right? So I know that the magnitude for that pull vector is 120, and the angle for that pull vector is 38. So I can resolve that pull vector into a component form vector by doing magnitude times cosine of the angle, comma, magnitude of the vector times sine of the angle. And likewise, for the ramp, we're given that the ramp is angle is 25 degrees, but we're not told the magnitude for the ramp. Since we're not told, we're going to fix it at 1. We're going to choose the magnitude for the ramp to be 1, which means that that component form for the ramp is just 1 times cosine 25, comma 1 times sine 25. I'm just going to drop the ones. And now what we're looking for is like this projection, right? Where I'm going to project that angle or that vector P down onto my vector R, and I want the magnitude of that projection. Now, since we're projecting onto a unit vector, this process is much easier. It's just going to be the absolute value of the dot product of P and R. That was something we proved in our last lesson. Okay, so that's just going to be 120 cosine 38 times cosine 25 plus 120 sine 38 times sine 25. So I get 116.9. And if I think about this reasonably, that seems reasonable, right? If I'm looking at those two, I'm almost pulling in the exact same angle as the ramp, right? 38 degrees is pretty darn close to 25 degrees. If it was exactly the same angle, I'd expect all 120 pounds of force that I'm pulling to be exerted on the crate in the same direction as the ramp. Here I'm getting almost all of it because I'm pulling at almost the same angle, which is what I'm seeing here, which I think makes good intuitive sense to me. So I'm pretty happy with that answer. Elena, was that?
Yeah.
Did that help?
Yeah.
Okay. Rita.
So for like the dot product way, so like the only two times you use it is if it's like a unit vector.
So if you're projecting onto a unit vector,
Okay.
you can just shortcut to a dot
And
product.
if it's like they don't give you the length. Like,
That's how you can assume that it's a unit
oh,
vector,
okay.
right?
Okay.
Yep. So if you're not given the length of the ramp, the vector you're projecting onto, you can assume that that length is 1. And when the length is 1, you can take that shortcut.
Thank you.
Yeah. So if you're not given any information about the length of the ramp or the dimensions for the ramp, it's your choice. Choose it to be 1 because it makes life like massively easier. Casey.
Can we do 69?
Sure. Okay. So here it asks to find a possible vector line equation in IB component form for the line that intersects the following points. So I underline possible here because there are infinitely many answers. The two things I need for this is I need a slope vector. So I'll start by calculating the slope. So 4 minus 5 over 3 minus a negative 2. So that's negative 1/5. So my slope vector that we use the letter V to represent is going to be 5, negative 1. Remember, because this is change in Y over change in X. And then the other part I need for my IB vector equation for a line is a point vector. Well, I could use either negative 2, 5 or 3, 4. I could find some other point that lies on those lines, but why would you do that? Right? Like use one of the two. And that's all we need. So I have R0 plus VT. And that'll do it. Okay? Giselle. Sure. Okay. So here it says determine whether the following point lies on the line. So this is like if I take the point 5, 2, I'm just going to think about it as the point vector 5, 2. Okay with that, Giselle? So what I want to do then, if I plug 5, 2 in for R, I want to determine if there's some value of t that allows me to get the vector 5, 2. So I'm going to write the equation 5 equals negative 3 plus negative 2t. And solve that for t. And then I'm going to write the equation 2 equals 14 plus 3t. And since I get the same value of t, my answer is yes. Of course that point lies on there because the parameter I need to choose to get that point vector out of that is -4. If the values were different, I would say no. And even a little bit different is enough. They have to be identical. Brayden? Sure. Cool with that? Easier than you thought?
Yeah.
It's okay. Again, like, for the most part, this chapter, while the calculations we're doing are pretty simple, like, there's a lot of vocabulary, there's a lot of notation. It makes it kind of difficult to really understand what you need to do something, or what's the easiest way to do it, right? But once you kind of get that everything sorted, it's kind of straightforward, right? This would be the same as like the question like, is, like 3, 5 on the line, y equals 3x plus 2. How would we check that? Well, you plug in like, the x and y and see if they're equal, right? Same idea. In this case, the answer is obviously no. But it's kind of the same question, right? It's like an Algebra 1 question, or just using a different language to do it. Kind of. Is that okay? Again, as much as I can, I want to draw back analogies to the stuff that we're hopefully feel pretty familiar with. Okay. Does that feel better on questions on stuffs? Anybody else before we move on? Okay. I want to talk real briefly about the next lesson, then we'll do the homework quiz. So the next lesson, we're just going to talk about three-dimensional stuff, like the three-dimensional coordinate system. This is in the middle of the page, it is, isn't it? That's kind of annoying. Okay. So when we talk about a three-dimensional coordinate system, we're talking about an ordered triple. We give the coordinates for an ordered triple as an x coordinate, a y coordinate, and a z coordinate. Visually, what we're talking about is now three axes. So you have like length, width, and depth. So we can still kind of draw this in a two-dimensional space, even though there's a three-dimensional axis. But we have to kind of use some imagination. So what the three-dimensional axis kind of looks like when we sketch it is this. You have to use a little bit of your imagination. Imagine that x-axis like pointing out of the sheet of paper towards you. So like imagine that kind of coming out of the wall. And usually we just draw, when we draw these things, we just draw the positive side. So this is like the positive end of each of these axes. So like that would be like the negative end. We usually don't draw the negative end in unless we have to. just for keeping everything a little bit cleaner. Is everybody okay with that? Keep in mind here, though, that whoever did this was pretty rude. Instead of putting the z-axis pointing straight out of the paper, the convention here is that what was the y-axis in 2 dimensions we call z, what was the x-axis in 2 dimensions we're calling y, and the new axis that we would hope to be called z we're going to call x, which is kind of rude, but that's just the convention that settled on, and you can't change that. So let's show you guys how to graph a point in 3 dimensions. So the way we do this is we want to start by just plotting the point 3, 2. So I'm going to move 3 tick marks in the x direction and 2 tick marks in the y direction, right? So I'm now going to build like a parallelogram. So that's like the point 3, 2. Everybody okay with that? What I'm going to do next is I'm going to go 5 units up on the x-axis or on the z-axis, and I'm going to do that from each of the 4 points or 4 corners of my parallelogram. And I'm always going to start with the corner that's at the origin. So if I eyeball that, looks something like this. Is everybody okay with the parallelogram that I've drawn there? So where is the point 3, 2, 5 then? So if I take the point 3, 2 and I project it up into 3 dimensions, that spot there is the point 3, 2, 5. So basically what I do is I start by building a parallelogram whose side lengths are the x and y coordinates, right? So I've made a little parallelogram, a plane, and then I lift that plane, whatever the z coordinate is, and that'll create the proper vertex of that is the point in 3 dimensions. Should we do that one more time? All right. So first thing I'm going to do is worry about the point 2, -3. So I'm going to have to extend the y-axis in the negative direction, right? I'm going to put 2 tick marks on the x-axis, and then 3 tick marks on the y-axis. And so like that's going to be then like my point 2, -3. So far, so good. Now going to lift that plane in the z direction 4 units. So 1, 2, 3, 4. So there's lifting the first point. There's lifting the second point. And we'll lift this one. I'm just kind of eyeballing that. And then I'm going to lift that point. Again, just kind of eyeballing that. So there's my 3-dimensional plane. And the point that was the point 2, -3, the lifted version of that point is my point 2, -3, 4. Now, suppose for example, instead we had asked you to plot the vector 2, -3, 4. How does that change? There's one additional step. So that I have to draw the head and tail of the vector. So I start at the origin, draw to the point, the head goes at the point, the tail's at the origin. Whoop-diddy-doo! Right? Now, I will tell you, when I ask kids or students to graph the vector on the test, half of you will forget to draw the vector line. You'll plot the point just fine, and then you forget to draw the vector. I know. I'm warning you. I'm warning you. It won't matter. You'll still forget. It's okay, though. All right. The last two things that I want to talk about with the 3-dimensional axis is just what a distance looks like, a length looks like, and a midpoint. How do you do that in 3 dimensions? Well, we're just going to appropriately modify our distance formula and our midpoint formula. So notice the distance formula is exactly the same, but we have a third component in there for the z's. And our midpoint formula is exactly the same, except we have a third component in there for the z's. Oh, just do it the same way. Oh, well, that's really pretty easy. So let's do one quick numeric example, and that's it for this section. So let's do the distance first. So the distance is going to be the square root of x1 minus x2 plus y1 minus y2 plus z1 minus z2. So when I do that, I get about, or I should say equals, let's see, that's 14 squared, 13 squared, 13 squared, 534, I think. Yeah, I think so. If I want to do the midpoint then, that's going to be x1 plus x2 divided by 2, y1 plus y2 divided by 2, and then z1 plus z2 divided by 2. So that's going to be -1, -1.5, and then positive 4.5. Woo! Mr. Kulik, I like it. That was pretty easy. Yeah, dude. So the homework that corresponds to this section is 77 through 88. Pay special attention to the graphing practices, right? That's the part that's typically the trickiest for students. The midpoint and distance formula, it's like we're doing this plugging stuff into a formula. It's the exact same formula as before, just like an extra component because there's a third dimension. Whoop-de-doo-doo. That's all I got for you guys. Sound okay? We'll do the homework quiz to finish us out. Ooh, this is a short period, isn't it? I forgot about that. Well, we'll figure it out.
Oh, wait, yeah.
How much are we short? We still have 20 minutes?
No, 1 minus 4 is 5 plus 2 is